Now we're set. Awesome. Okay, so how's this? Yeah. So what had we seen so far? Well, we saw initialization. We saw initialization. We saw evaluation, selection, crossover, and mutation. But remember, for each of those individual bits, I just did tournament selection because. I did bit flip mutation because. That is not the right thing to do. That is a thing that you do. With all this stuff, there's no right way to do it. And like I've been saying several times in the course, when you're implementing these things, be creative. Come up with whatever strategies you want. I don't care how bad it is, just have fun with it. All right? But all of that just describes one iteration. So initialization is initialization. Then evaluation, we evaluate how good the chromosomes are. Selection, where you select those that you have a higher probability to select those that are more fit, but there's still a chance to select not particularly fit individuals because we were talking about diversity. Diversity is good and important. And then we've got our genetic operators, both crossover and mutation. We saw with the specific examples, I realize I'm not actually displaying any content. There, that's much better. There we go. We saw that with that crossover, it was really good at exchanging information between chromosomes, but it had no way to like create new information with this representation and how the crossover was done. So that's where mutation came in because it gave us the ability to add new information to the chromosome. We saw that example right here, right? Where, well, index 1, there's no 1 there. Meaning, no matter how you do crossover here with that 1-point crossover, you can't possibly get a 1 in index 1, meaning there'd be no way to find the optimal solution. So this is why we added in the mutation. It actually added a way to explore the search space a little bit more and add new information. But that's one iteration. We want to repeat this process a lot. But when do we stop? Do we stop once we find the optimal solution? Sure, maybe for some problems, but for other problems like we were talking, expecting to find the optimal solution is probably a pipe dream, not happening. Do we stop after maybe the population has converged? Converge is a fancy way of just saying where they all kind of become the same thing and the diversity in the population is really low and you're not really going to find anything new. After it's converged, how about after no improvements to any candidate solution has happened over the past so many generations? Maybe it's after some predetermined number of generations is set, whatever you want. For me, what I did here is I just hard-coded how many generations am I going to run for. I'm going to run for 1,000 generations and hope I get a good solution. It's really simple. It'll work. But again, this isn't the right way to do it. This is a way to do it. So if we have a look, here is just my basic generation loop. So after initialization is done, for each generation and generations, I create the population fitness. It's an empty list. Evaluate the fitness of each chromosome. This is just bookkeeping. For keeping track of the best. It's just a list to keep track of the best fitness and the population's average fitness for each generation. We can plot it later and look at it and see what happens. Selection, crossover, mutation, and then once we're done, that mating pool, which was that temporary holding place for the chromosomes that were going to go to the next generation, we actually make the population be that mating pool. And then repeat. Repeat until however many generations are done. You see I have it set as a constant. I put in a value and I hit run and I'm good. And then once that's done, after all that's done, what do we do? Well, if you look at this loop, the way I have it coded here is the first thing I do is evaluate the fitness. And the last thing I do is the variation operators, meaning the chromosomes would have changed before evaluation was done for the last time. Meaning, so I did evaluation, I applied the genetic operators, I go back to the top of the loop and the loop's done. Meaning the variation operators were done, but I never calculated the fitness of the population after that last round of variation operators. That's all I mean. So what I'll do is I just do one more round of that. I print the population fitness, so that'll just be a list of the fitness values. I print the population, that'll just be a list of lists of zeros and ones. I print, and then I append the bookkeeping stuff. Good. And that's it. That's the GA. That's it. And here, no. Here, let's see for a moment here. Let me see. How do I increase the font size? Settings. Editor, font, 13. Is that much better? Yeah, that's better than before, right? Yeah. Okay, so what do we see? Here's the code. Well, at the top, I've just got some docstring to describe what's going on. What does it matter about here? These are just my hyperparameters or constants I have set. I selected those values. They're arbitrary. We can play with them all we want. I wrote the fitness function. Ignore this one here for a moment. We're going to talk about it in a moment. And then here, this is basically like my main. And this is it. Bookkeeping stuff, initialization. This is the generation loop right here. Evaluate the fitness, update the bookkeeping. Selection, crossover, mutation, and the generation loop. And then finally, here's the ending stuff. Population fitness, evaluate it again, print it out, update the max fitness and whatnot. And then there's some commented out stuff here that we will play with in a moment. Whoops. Nope, what happened there? And any questions? Yeah.
Are you using IntelliJ? What are you using for PyCharm?
Here, I'm using PyCharm. I know it looks like IntelliJ, but that's because it's made by JetBrains. So it looks a lot like, you can even get like a Python plugin for IntelliJ that just basically makes it PyCharm. But I recommend, if you don't, if you like these IDEs, by the way, what you want to actually install is, you don't want to install any one of the individual, I don't know why it's not opening. You don't want to install any of the individual IDEs from JetBrains. What you want to do is you want to install the JetBrains toolbox. And then from there, you can select, I don't know what's going on here. Try again. I might have to like update my credentials or something, I don't know. It's probably got an update, yeah. And then from here, you can download any of the IDEs you want. So just FYI. Got it. Pardon? Yes. If you're a student, it's free. And if you're, so there's like PyCharm and IntelliJ. So PyCharm is it's an IDE for Python. IntelliJ is an IDE for Java. There's another one down. I mean, all of these are just various IDEs for various situations. Dataspell I haven't played with yet, but I think it looks pretty interesting. What's this one? A powerful for test automation. Interesting. C-Lion, that's like your C one. They're all very similar. They're made by JetBrains. These are arguably some of the best IDEs, if not the best IDEs there are right now. It's all free. All of these things have like a free version. I think C-Lion doesn't actually. But if you're a student, you can get like the premium version for free as well. Now, mind you, the premium versions of these things don't come with any bells and whistles you're going to want to use anyways. Like they're usually pretty sophisticated, heavy-duty stuff that like teams of software engineers will be using, so it doesn't make that much of a difference, but yeah.
And where do you find like the keys to get that? Do you need to email the school?
I think it'll just be like, here. Honestly, I don't remember, so let's find out. No, JetBrains, student, there. Free educational licenses, let's see. Well, hold on. That's for like institutions, I think. Where's like the sign up button? It's somewhere around here. Just literally do what I'm doing. Just poke around, you'll find it. If I remember correctly, it's just like when I created my account, I specified like, well, you know, I work at a university, so, and then they're like, oh, here's your free license. I just have to like resubmit it once a year or something, but whatever. If you've got the toolbox, it'll probably help you too. If you like PyCharm, use PyCharm. If you like VS Code, use VS Code. If you like what other IDE, use whatever IDE. If you hate IDEs and you like working in a terminal in an interpreter, go for it. Doesn't really matter. Do whatever you want. I'm just going to use PyCharm because I've got PyCharm here. Cool. So here's my plan. What I'm going to do is I'm going to run this a few times, and we're just going to like see what happens. Okay? Then the next topic is, the point of the next topic is here actually I think I do this one. You are going to take that code and you're going to play with it. We'll do it for the rest of the day, maybe even tomorrow, I don't know. We'll do it for however long we want to do it, where you just play with it. I've got a series of like exercises if this is a lab. But the point is, I want you to get your hands dirty with the genetic algorithm. I want you to just dick around with it, see what you can do, see what happens, see if you change this, what does it do, see if you change that, what does it mean, and so on. That's the point. But in order to do that, we'll have to get the code on your computer, and the easiest way to do that is through GitHub, through the create a fork. But I'll walk you through that just for ease. Cool. All right, so first things first. Here, I'm just going to lower this, and I'm just going to sit down to just play with the code. Oh, here's 161 content, in case you're interested. All right. So remember, first of all, here, yeah, install requirements, install. Remember that these algorithms are, we like to use the word stochastic. Who here knows what stochastic means? It's a really fancy word that just means random. But we like the word stochastic because it sounds better. That's really it. It's stochastic. There's a lot of randomness involved here. We randomly create the population. We evaluate, that's deterministic. We randomly select. We randomly determine who's having the genetic operators applied to them, and we randomly determine how those are applied. There's a lot of randomness, meaning every time you hit run, you should not expect the same results. You're going to get wildly different results, and that's normal. That's what's to be expected. So be aware of that. If you hit run and your neighbor hits run and you get different results, don't think, oh no, what did I do wrong? No, that's normal. That's to be expected. All right, things are just updating. So here, first things first, here's what we're going to run it with. We're going to evolve bit strings of length 10. Right? So the most optimal solution is a list of 10 ones. We can make this bigger. If we make it bigger, here's a trivia question for you. If we make it bigger, is the problem going to get harder or easier? It's not a trick question. Harder, obviously. Population size, I have it set to 10. This is very little. You typically have populations way bigger than 10, so it's very little, but it's just here for the sake of showing you stuff. Tournament size is 2. I could make it 7. I can make it 3. Here I have it 2. I can make it 1 if I want, but then it's just basically random selection. There's no selection pressure, if you remember what I was talking about. Basically, if we have a tournament size of 1, we randomly select an index and then take the best index, take the chromosome with the best fitness of the selected indices. Well, I only selected 1 index, so it's just whatever one I picked. If I pick 2 indices, I take whichever one of the 2 that has the best. So I'm more likely to pick one that has a better fitness than if I just picked 1, right? If I picked 7, of the 7 I selected, I'd take the top 1. Well, now I'm even more likely to pick those that have a higher fitness from the population. Generations, this is the number of times I'm going to run that loop, 25. That's hilariously low. A crossover rate of 7.7, 70%. That's fairly common. And a mutation rate of 10%. That's also fairly common. So these are the settings I have. And let's hit run. Let's see what happens. I'll just do it here. Yeah, run. Is it running? Okay. So this was the result. This is the fitness of all 10 things in the population. First of all, what is the optimal solution? What is 2 to the power of 10? 1024, but of course, that's unique values. So the binary, of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to decimal. It's 1023, right? Because there's 1024 unique values, but that also includes 0. So the max value that we could get, is 1023. And look, the last chromosome in our population actually got the optimal result. All of the other ones actually were 1007, which is interesting. They were all, in fact, they were all the same, but they were all not quite optimal because we're missing a 1 here, we can see. If we go all the way to the end, there, this one, it's all 1s. Hooray, we're happy, right? Yay. Let's run it again, see what happens. Feels like it's taken really long. Shouldn't take that long. All right, this one got all, one of them. 1019, yeah, this one. We were missing a 1 there, right? Cool. So let's make the problem harder. Let's make it like 32, right? A 32-bit integer. Let's hit run. So obviously, like we were saying, this is now going to be a harder version of the problem. Oh, there we go. Well, what is the optimal? What is the best? What is 2 to the power of 32? So 4,294,967,295, right? That would be the biggest because of 0. And remember, these are unsigned integers. So what is the last number? 295 would be 295, 295, 295, 295, 295. We can clearly see we haven't found the optimal, right? It's not the optimal number, and we can see here is an example. We're missing a 1 there, we're missing a 1 there, 1 there, 1 there, 1 there, 1 there, 1 there, 1 there. We're missing a bunch of 1s. So, okay, great. But obviously, this isn't particularly easy to see what's going on. So I'm going to run this again, except instead of just looking at the results here, we're going to plot the results, and we're going to, so we can see what's actually happened here. Let's see. Man, Okay, so that's what we would call a learning curve. Who here's heard that phrase before, learning curve, right? You see these in like deep learning and neural networks as well too. Basically, when you have an iterative learning process, we're just going to plot like, here this is like, it's not accuracy here, right? It's fitness. But basically, this is the learning curve. We want to see it go. And this is typical of a lot of learning curves. If you look at the average fitness, we see there's a rapid increase and then there's like a slower increase. Very common. This is what you see. So, okay, cool. This is great. 32-bit integer. So, I let it run for 25 generations. Yeah, that's pretty low. Let's let it run for 100. If we let it run for 100, should we be more likely to get better quality results? Or, yeah, of course. Obviously, if we let it run longer, we're probably going to get better results. So, let's run it. All right, well, there we go. It's a different learning curve. And, I mean, we're getting better, right? We're missing 1, 2, 3. Look, we're really close. We're getting close, right? But the population size was 10. Let's make the population size 50. If we make the population size 50, would we expect this to have a positive or negative impact on the quality of the results? What's your intuition tell you? Negative. Why negative? Intuition. There you go. That's a great answer. Anyone else? Any ideas?
I'm not very certain, but I was going to guess positive just because there'd be more diversity. I don't know if that's
A potential for more diversity? Yeah, okay, I hear you. Now, first of all, okay, is this going to make it take longer to run or less time to run? Longer. Of course, there's more to evaluate. And if it wasn't obvious, the fitness evaluation is the slowest part of every evolutionary algorithm, evaluating how good each chromosome is. So let's hit run. Give it a second. Oh, look at that. It looks like we actually got the best. Looks like we got the optimal solution. Let's run it again. Maybe we just got really lucky. Well, it's looking pretty good. So typically, with a higher population, you are seeing better quality results. Usually. But there is going to be a point of diminishing returns, if not potentially negative impact, depending on how big you make it. If I made this population gigantic, that could end up having negative effects. Oh, yeah, I hit run again, but cool, great. So this is actually learning pretty darn quickly. I mean, we can see like we're getting near, like only after like 20 generations, we're getting quite near optimal at least. So let's make it a 64. Anything beyond that, our computers are going to be unhappy with. So, okay, clearly here, we're not quite at the optimal. Okay, but let's just make it run for even more generations. Let's make it that might take a while. Let's make it take 500 generations. Let's let it run 5 times longer. So we'll just have to wait a moment. Oh, okay. It's looking pretty good. It looks like that's optimal. What is 2 to the 64? Okay, well, I want all the digits. Come on. 616 looks like it's the end, so 615, yeah. It looks like we're finding the optimal solution. This is fantastic. 64. I don't think the computer's going to be happy if I make it much bigger, because of course we're going to run into issues with. No, all right, it's good. It's happy. And it looks like. I mean. That looks like it's probably the optimal solution.
I think there's 1 0 near the end.
Oh no, really? Oh, son of a bitch. There we go. Yeah, look at that. Nasty little guy there. And it looks like they've actually, the population has, this is what we would call like converged. We can see, like looking at this line, there was a lot of quick learning. Let me hit run again. There was rapid learning, but then we didn't really see any progress. That's when we would say like, well, it's converged. There's no real improvements taking place. Once again, I wonder if there's any zeros here. No, that one looks like we got it. So this is actually working remarkably well. What happens if we make the mutation rate like 0? Let's see what happens. Yeah. Look at that. The only thing I did is I changed mutation from 10% to 0%. Look. Clearly that's not the best result, right? We can see a bunch of zeros there. And we know why. That mutation is very important. What happens if we make crossover really low? I'm curious. Oh, looks like we got pretty lucky here. It's not a bad result, at least. It looks like it's not quite optimal from what I see, but look at that. Darn close. So it looks like on this particular problem we're getting lucky. We can get away with a very low crossover rate. Once again, it doesn't look like it's the optimal solution, but we're getting there. I wonder what happens if we increase this. Let's make it like, our populations, let's make it like 5. Let's see what happens. So right now, I'm just playing. I'm just poking around, seeing how it impacts the results. This looks like it's the optimal solution. What happens if we make it 50? Let's make it 100. A little oversample. Oh, looks like we got the best one. But you'll notice that the difference between the average population fitness and the best of the population fitness, I mean, it looks like there's like no difference there, right? They're basically on top of each other. Where if we put this back to 2, let's see what it looks like. Maybe it's hard to tell at this scale, but let's see. Yeah, it's hard to tell at this scale. Let's go back to like 32, population size 10, 50 generations. Let's look here. Okay, no, that's a funny looking one. Let's run it again. No, it's making me a liar. Well, maybe not on this, but maybe we make it a little bit more difficult. 64. Well, at the very least, you see some of the difference, right? The average population fitness and the best, there is a difference. But it looks like the population does converge pretty quickly. Here, we can clearly see, oh, one candidate solution like improved, but then the population kind of moved towards that one best thing. So the population was affected by one good thing. See what happens if we make tournament select size 1. All right, well, clearly we're not getting anywhere near optimal. Let's go back to 32. And that's because like we've got no selection pressure. We're just randomly picking candidate solutions. There's nothing really guiding it towards goodness. Yeah.
So tournament size is the number of participants in the tournament, right?
Yeah, so there's the population, and then for each selection, let's just go over it again because it can be a little funny. And again, I really want to emphasize this is just one selection strategy. I have, what do I have? Population size of 10. My tournament size is K. I pick K, I randomly pick K indices. It is possible to pick the same index multiple times because it's randomly selected, but for the sake of simplicity, I pick K. Of those k, I'm going to take the best one. And I'm going to put it aside. And then I'm going to repeat that process over and over and over until I've got my mating pool full. As k gets bigger, I'm more likely to select the good candidate solution from the population, right? If k is very small, like 1, I'm basically randomly picking, I'm randomly picking something to make it to the next generation, basically. I'm picking 1 and taking the best of that 1. It's the 1. And we could see, yeah, it has an impact. All right, great. So I'm just going to Control Z everything, go back to the initial settings I had. Stop. I don't know what that is. I don't know what it was doing. I don't know. Interesting. Yeah, so there we go. Let's close this bit. All right. Any questions about that poking around I just did? Nothing? All right, here's what we're going to do next. So, if you are at the course, okay, raise your hand if you got GitHub Desktop downloaded. Did you have your hand up?
Yeah, I was having a question.
Yeah, what's up?
Can you go back to the code?
This code?
Yeah.
Yeah.
Why is it must be multiplier 2?
So this is because I'm lazy. Here's why. Because I could fix this really easily, but I'm too lazy to do it. When I am doing crossover, it's all because of crossover. When I'm doing crossover, I'm always selecting neighboring pairs. And if the population size is not a multiple of 2, I'm going to run into an issue of selecting pairs. So I could fix this really easily, or I could just say, make population size a multiple of 2. Good catch, but it really is just, I'm that lazy. You had a question too?
Oh, no.
Oh, I thought your hand was up. Okay.
No, it's when you're asking who got the GitHub.
Okay. Did anyone not get GitHub Desktop installed? I think it's available on Mac. I just can't confirm that. Anyone in here on a Mac get it installed? You got it? Perfect. Good stuff. So, you installed GitHub Desktop? Awesome. So, let's go. If you go to the course website, let's go to the home, the main page. Here, at the very top, you will see a link right here. The content used to generate the course can be found on GitHub. And here it is. This is all the course content. I'm actively still updating this. But this is the course content. It includes everything I have here, right? And so here's the code. Here's unit tests for the code. And it actually also includes all the topics. So if we go to GA, simple GA, this is what was used to generate the course content. Cool? Now that part's not necessarily particularly interesting to you, but okay, follow along with me. Go here. If you're not on this page right now, get to this page. And if you don't remember how, just go to the course website, and if you can't remember what that is, it's just csci340.com. You go there. It'll redirect you to this one. And then right here is the link to the GitHub. All right? Raise your hand when you are there. And put your hand up and leave it up so I know. Okay, so we'll just wait a moment till everyone's on the same page. Literally. You can put your hand down now. And then once you're there, we're going to download, or no, we're not going to download. We're going to go, is that, all right. So is anyone not there yet? You're still working on getting there? Are you on the page? Okay. So now what you're going to do is you're going to go here and you're going to click this button that says fork. This is assuming you are logged into GitHub. When you click fork, for me it won't really do anything because I'm the owner of the repo. But fork basically means you're going to basically copy this repo to your account. All right? Raise your hand when you're done forking it. Really high, I want to see everyone keep your hand up.
Just click like create fork once you.
That's the one. Okay, how about this? Raise your hand if you're not done that yet. Okay, we'll give you a second. You're moving, or are you stuck on something funny?
Am I supposed to be doing this in the app?
No. Just on the web page.
It's forked then.
Then you're forked? Awesome. Awesome. Great. So now this means on your GitHub, you should have it. Meaning, you should be able to go to your profile and under repos, you should be able to find CS4XX evolutionary computation. And you click it. So you go to your fork. There are 1, 2, 3, 4, 5, 6, 7, 8 people in here, and there's a total of 9 forks. Perfect. That's exactly what we want. Oops. No. I want to see the forks. No. How do I see who's forked it? Come on. There's a way to do it, I swear. I just can't remember right now. All right, not too important, I suppose.
I think the 9th hole on the side. Go down a little.
This one?
No, go down a little. Like 3, 1, saying the 9th hole. Down.
This?
Down.
What?
Like at the bottom.
Oh my God. Okay, currently it says there's only one fork. Okay, clearly this is not updated. Period, 2 years. This is forks. All right, well, who knows how long that takes to actually update. Whatever, there's 9 forks. Now, if you go to your GitHub desktop, you will see something like this. All right? If you have not had it raise your hand if your GitHub desktop is not logged into your GitHub account. It's not? You don't know?
I thought it was.
You thought it was? Let's have a look. I really do want to just make sure everyone's on the same page. You don't want? Let's get started. Create a tutorial.
That's exactly where I'm at.
It looks like, oh no, clone. Okay, no, you're good. So here's what you're going to probably do. Clone a repo. Yeah, you're going to want to clone a repo.
So do I just copy this URL?
Actually, you probably shouldn't even have to do it. So say clone a repo from the internet. URL, github.com. You should have a list from your repositories. Yeah, there it is. Yeah.
Tell them what.
Yeah. So it was not that obvious, but if you're on a landing page that says clone repo, you should see something here. If you don't see anything, click the little refresh, and you can see all your repos and whatnot. And look for CSCI or CS3 or 4XX, whatever I called it. Click it and say clone. It's probably going to ask you where you want to save it and whatnot. I'm lazy. Mine's just on my desktop right here. Yeah. Is everyone good? You know what? Because I want to make sure everyone's happy and on the same page, just go along and just make sure everything seems good so we're not hitting any hiccups as we go. Looks good. No local changes. Yeah, that looks good. 340 or sorry, 4XX, 4XX. You'll notice mine, I've got the dark theme on. 4XX. It's actively cloning. 4XX, looking good.
So I just got this one I cloned it. Not, I guess I'd say for my own purposes.
Probably, yeah. Just say for your own it really, that's not going to matter. That's probably just like some basic settings on how it's probably going to want to act by default. 4xx. 4xx, looking good. Perfect. So now you've got it. So now, in your IDE of choice, raise your hand if you have a Python IDE installed on your computer actively. Okay, so it looks like everyone. Okay, good. Whichever your favorite is, go to that IDE and open up the project by navigating to wherever the hell you put CSCI 4xx. So for me, I would do like, I mean, I already have it open, but for the sake of just showing you, let's close project. So I would, open project, I'd go navigate. I know I put it on my desktop, so I just set it, open, and there we go. We're there. Yeah? Cannot run Git. Git's not installed. Sure. Now, who here is using PyCharm? One person. Two people. Okay, what IDE are you using? VS Code. Okay, cool. Now, I don't use VS Code. I know a lot of people do. There's nothing wrong with it. I'm not familiar with how to get it to do what it's got to do. But there's going to be a way. So who here knows what a Python virtual environment is? Okay, one person, so I'll explain it. You know how, like with Python, one of the big things about Python is, oh, it's great. There's the standard library with Python, so it's got all the stuff that you get. But of course, there's pip, right? You know pip. Like if you ever want to install anything fancy, you just like pip install whatever, and bingo bango, it's there. You're happy. The problem with that is, well, certain projects that you're working on might need a version of NumPy that's different than a version of NumPy in another project that's different than a version of NumPy in another project, and then the other one needs SciPy, but that version might conflict with a different version of NumPy in a different. So you end up with all these dependency issues. Turns into a nightmare. So what we do instead is we create virtual environments, which is basically you create this little an environment that starts with like a fresh Python install every time. And then you install all the dependencies you need to that particular environment. Then, when you're working on that project, you're in that environment. When you want to change projects, you just change the environment so you don't end up having any of these dependency issues. So that's the purpose of a virtual environment. It's nice. For me, an IntelliJ, depending on if I'm on Windows or I'm going to guess if you're on Mac, you're going to want the bash one, but I'm actually not 100% sure. I haven't tried it on a Mac. You're going to want to run two of these things. Okay. Here's a question. Raise your hand if you're using VS Code. Okay. For those of you using VS Code, when you open the project, was there a pop-up anywhere saying like missing dependencies? No? Okay, so let me see what it looks like. Hey. We are out of time, so yeah, no missing dependencies. So maybe click README real quick. I just want to see. We'll end here for today. Yeah, I don't know. Okay, cool. I'll look into it later because I want to make sure you can get all set up. But this is where we'll end today, and then we'll pick up whenever next class is. Cool. Any last questions? All right, cool.